All right, so thank you very much both for the introduction, the invitation again. So this will be an introduction to the Gaussian free field. So as I think I've hinted at yesterday, the Gaussian free field really is the sort of canonical notion of random function on a domain in the plane, where function has to be taken in quotation marks because it's not actually a function. And because there's sort of quite a bit of analytic subtleties in sort of defining this object, I thought it might make sense to start this introduction by saying a few things in the discrete case where things are sort of, there's much less technical apparatus and much less technical or analytic subtleties. And sort of it's a bit easier to get an intuition, I think. So, so I'll try and start with that. So I'm not completely sure what is the background of everyone. Of course, if there are questions, it's very important that you ask me and ask me to slow down. And even if the question is not well formulated, I think it's good to do that. So what's going to be the setup? So I'm going to imagine that I have a graph, G, which could be anything. So a set of vertices and edges, let's say finite, but it doesn't really have to be. And I'm going to say that this vertex set actually consists of two things. One which will be the kind of the true vertices of this graph, and something else which I'll call the boundary of this graph. And if you're thinking of, if you want to think of an example, you can think that this is the vertex set of a grid in 2D. And maybe all the vertices on the boundary are wired, and that's what I called this boundary vertex. So you can imagine that I've all joined these things together. Okay, I'm not going to write it all, and that's what I call the boundary vertex. And we're also going to imagine that this graph is weighted, and so on each edge, xy. There is a weight qxy, it's undirected, so qxy is the same as qyx, and it's strictly positive, otherwise I don't include the edge in the graph. Okay, and so when you have an object like that, there is a natural random walk associated with that. So so the random walk in continuous time on G. So this is simply this is a Markov chain. A Markov chain with rates of transition from x to y given by exactly this weight, qxy. And so in every dt unit of time, there is a chance approximately qxy times dt that the random walk will make a jump from x to y, and this is Markovian. Okay, if you're not super familiar with random walks in continuous time, there's really not much loss in thinking that we're working in discrete time, and maybe to avoid slight annoyances, then it's better to imagine that this graph has a constant degree, because then otherwise you have to normalize by the degree, and it gets a bit messy. But in continuous time, things work very well, and so this is the setup I'm going to use. So I'm going to call that xt. Oh, maybe I should say that, that after touching the boundary, the walk does not move anymore. So this boundary vertex partial is a trap for the random walk. Okay, so that's the random walk. And associated with that, I can construct the green function, which plays a role in this story of Gaussian free field. So the green function on G is defined to be so G of xy. G is maybe not a great name. How about little g? G of x and y is defined to be the expected amount of time. So you would start the random walk from the vertex x, and you ask yourself, what is the total amount of time that the random walk will spend at the vertex y before being killed? So I integrate between 0 and infinity. And that's what we call the vertex y. Okay, so if x and y are very close to one another, then maybe gxy is quite big. Otherwise, it tends to be quite small. So it measures the expected amount of time that the walk spends at y if you start from x. And it is not hard to see. So G is symmetric. So G of x and y, I'm not sure what is this light. It's a projector maybe, yeah. So G is symmetric, so gxy is equal to gyx. And that's because the walk itself has properties of reversibility. So G is symmetric. What's that? Oh, yeah, but okay, so as soon as x is the boundary, then the walk is trapped, and G of the boundary and any other vertex will be 0, so, okay. Yes, maybe, yeah, that's right. It's symmetric when we restrict it to, yeah, maybe I should say that, to the, okay, we only care about it on the true graph, basically, away from the boundary. Okay, so G is symmetric, and we also can say that all its eigenvalues are, if I think of it as a matrix, all its eigenvalues are positive. And this is related to the fact, if you like, that G is the inverse of the Laplacian. So maybe I'll say it without proving it. G is the inverse of the Laplacian, and all the eigenvalues of the Laplacian are positive. Or another way to put it is that if you have a transition matrix on the graph, a stochastic matrix, then all its eigenvalues are strictly less than 1. Okay. Okay, so all the eigenvalues are positive, and that makes G a symmetric positive definite matrix. And so I can use it, so it's a valid choice of a covariance. So the definition of the discrete GFF, so this is going to be phi of x. You can either include the boundary vertex or not, but let's include it, is the Gaussian vector, centered Gaussian vector, is low. Okay, so I'll write it like that. So n for normal, for Gaussian, which means 0. And all I need to tell you is the covariance matrix, and this covariance matrix is precisely G of x and y. So the fact that we have killed the walk when it touches the boundary is what makes the eigenvalue strictly positive. That's why the Laplacian is invertible. And so because it's a symmetric positive definite, I can consider a Gaussian law where that's where this G matrix, the green function, is really the covariance of this. Okay, so of this vector. So what we're saying is that points that are nearby, they are quite correlated, and points that are quite far away, they're more or less independent. Okay, but it's a Gaussian. So at every point on this graph, you've got a Gaussian random variable seated, and it's mean zero. And the way these Gaussian entries are correlated is via the green function, this discrete green function. Okay. Is that clear so far? Now, you know, when we introduce Gaussian vectors in first or second year probability, we usually tell them, we usually tell the students that you know, the covariance metric conveys much more information than the actual probability density function. And so we tell the students it's better to focus on the covariance matrix. But it turns out that in the case of the GFF, we get something very interesting when we describe the joint probability density function of the entries at all these points. So let me write this down. Maybe it's a theorem. So the joint law. So let's write. Maybe let us write. So let's enumerate all the vertices, all the true vertices of the graph V hat as x1 through xn, and right. So let me call these random variables y1 through yn. So the value of the fields at these vertices x1 through xn. Then the joint probability density function of y1 through yn at y1, little y1 through little yn is proportional to, so let me write it like that, f of y1 through yn. Maybe I move to the next board. So f of y1 through yn. So it's proportional to that, which is the exponential of minus a quarter sum over I, a neighbor of j. So maybe I write it ij such that xi is a neighbor of xj, or maybe I don't even need to write this actually. Let's not write it. And we will have q xi xj, so it's 0 if I and j are not neighbors, and yj minus yi squared. Okay, so that's a formula for the joint probability density function of all these Gaussian random variables. Normally, we tell the students, don't look at this, think instead of the covariance, because usually we get more information. But this is a formula from which we can infer a lot of properties. So that's a correct statement, but I think if you want to formulate it in a way that is more intuitive, so I would say that the probability, what this theorem is telling you, is the probability that you obtain a particular function phi is proportional to the exponential of minus 1/4. So sum over all the vertices. I can actually include v if I want. I can include the boundary. And phi of y minus phi of x squared. So, right, so we should understand this appropriately, the proper meaning of an expression like this. So this is an informal restatement, but the proper meaning of a statement like this is exactly what's written here. So you have to speak of the joint density function, the joint probability density function of the values at each of these points. But what we're saying is that the probability to obtain a particular function phi is proportional to the exponential minus a quarter, this sum, sum over all the vertices in the graph, qxy, phi of y minus phi of x squared. So you should think of this quantity as a discrete version of the integral of gradient phi squared. Okay, so what we're saying when we are saying something like this, we are saying a given function phi has a probability which is proportional to the exponential of minus the Dirichlet energy of phi. So this is the Dirichlet. Maybe you cannot read if I write here, but so let me stop after that. So,
how do you think about the Q's in the continuous case?
Yeah. So the Qxy is I mean, so in the case that normally you should keep in mind the Qxy will all be constant if we're speaking of the square grid. If you're changing x and y, it's a bit like changing the metric of the manifold, making x and y a bit closer together if you increase the rate of transition from x to y. And then it will be, you have to think of the Dirichlet energy with respect to the volume form associated with this change metric. So that's, at least that's the way I think of it. But I think there's no, not much loss if you think just in your head. We're working with the square lattice where all the weights are constant equal to 1. So why is this formula interesting? I'll say a word about the proof in a second, but I'm not going to prove it. But why is this formula interesting? It tells us something really fundamental about the GFF. So the GFF is a random function on V or V hat. It depends a bit on your point of view. It's going to be 0 almost surely on the boundary, okay, because the green function is 0 on the boundary. And so the Gaussian free field is a random function on the vertices of the graph, which tries to minimize this Dirichlet energy. So the greater the Dirichlet energy, the smaller the weight of this function, and so the less likely is this function. So the Gaussian free field tries very, very hard to keep this Dirichlet energy as small as it can. Okay? Now, you might remember from analysis, or if you haven't, it's not very hard to see, that the minimum of, if I give you some boundary conditions, and I try to minimize the Dirichlet energy, the minimum is achieved for functions that are harmonic. So if you like, you can think of the Gaussian free field as a random function which tries as hard as it can to be a harmonic function. Because if you try to deviate from harmonicity, it's exponentially penalized. Make sense? Okay, so the proof, how does it work? The proof is not complicated. It's more about translating things that we know from Gaussian vector, but you have to make the translation, and it takes a while, I think, to make the translation correctly. Well, we know that by definition, y1 through yn is jointly Gaussian. And we know its covariant matrix is given to us as the green function. So we know what will be the probability density function. So the probability density function, this symbol means proportional. I hope everyone knows that. This probability density function is proportional to the exponential of minus half y transpose sigma inverse y, where sigma, so this is the Gaussian density for a vector. That's really what we learn in first or second year probability if we learn about Gaussian vectors. And Yeah, so here, the matrix sigma is given to us as a green function. So it turns out, I've already alluded to it, the green function is the inverse of the Laplacian. So what you see here is really the Laplacian. And so we have something that looks like, okay, something like that. And there is, if you apply a discrete form of integration by part, you see that what you get is exactly, okay, so what comes out of this is exactly this. There's a factor half somewhere in the story. But okay, so that depends on normalization. So this is integration by part. So this formula kind of comes quite naturally when you think about it for a few minutes. And it tells you something very important about the Gaussian free field. Okay, so it's a random function, Gaussian at every point, which tries to be as close to a harmonic function as it can.
Is your integration by parts are saying that the matrix G is the square of the matrix G is the what?
The square of the matrix, no.
Sorry, not G, Q, or whatever it was called, R or Q.
Q, yeah.
Isn't that just saying that the matrix square of Q is?
No, it's really, it's the equivalent of, like basically, really, in maybe there's a minus that comes. It's the analog of this formula here. The discrete analog of this formula.
But I mean, the inverse of sigma is Q squared, more or less, right?
The inverse of sigma is Q, not Q squared.
Q.
It's a Laplacian. Q is a Laplacian. You have to think, yeah.
You said that this probability model sort of biases towards being harmonic.
Yes.
So in the finite case,
yes.
What is the measure of the space of harmonic functions? Is this quantity interesting?
Well,
I mean, you can look just at the set of harmonic functions on the
yeah.
finite. So it has a measure with respect to this probability.
Oh, I see. So, right. It will, so the almost surely the realization of the Gaussian free field will not be a harmonic function. So the set of harmonic functions actually has measure 0 for this probability law.
But for a finite graph, we'll have
even for a finite graph, because the values are if I look at the values at a point here, maybe it's 10.3, I don't know. So the values at the neighboring vertices, it's continuous, right? So because of this continuity, the fact that the law is continuous, there's probability 0 that that value happens to be exactly the average of the neighboring thing. But, so although it's almost surely not a harmonic function, it tries very hard to be harmonic. So, but it doesn't succeed in being harmonic. We will see in the continuum, it doesn't even succeed in being a function, so. But it tries, Does it make sense? That answers the question? Right. Okay, good. So, that's all I wanted to say in the discrete. Yeah.
I'm still stuck on my question. So, sigma inverse is really just Q.
Yes.
When you get on the nose that formula, right? You don't need any integration by parts, right? Because you get exactly this Q x, well, x, y, y.
Yeah, you need to say something because
just that when you interpret Q, if you would like to take a square root of Q and call that the derivative, the Dirac operator or whatever, or the what do you call it, the partial gradient, then you have some kind of integration by part, right?
I mean, I don't know. You need to say a little something. If you write down this expression, there is something that is really analogous to the integration by part formula. Maybe I can show you the calculation I have in mind. It's not a difficult computation, but there is a little trick. For instance, it wouldn't be true on non-reversible graph. If the weights were non-reversible, this wouldn't be true, for instance. Yeah. Yes, it is almost surely equal to 0 on the boundary. And that's a consequence of the fact that on the boundary, G of delta delta is 0, so the variance is 0, and the mean is 0. So I mean, you can include the boundary. You can include the boundary if you want, and then when you do, then this field is pinned on the boundary, and away from the boundary, it can deviate with correlations that are determined by this green function. But on the boundary, almost surely it's equal to 0. So I wanted to move to the continuum, but I think this is useful, this discrete thing, because in the continuum things are a lot more complicated. And we have to think a lot harder about analytic details. By the way, I didn't say it, but already on the discrete case, there is something interesting, which is that we can say more, there is it's not just that the density function is proportional to this exponential of minus the durational energy. We can compute also the partition function. So the factor, the normalizing factor that turns this probability density into a proper probability. And it turns out that the normalizing factor is the square root of the determinant of the of the inverse of sigma, which in this case turns out to be the square root of the determinant of the Laplacian. So I don't know whether there is really a reason why that's the case, and maybe there's a connection with the Daimler model. We were talking about it this morning with Cedric, and I don't really see why. But it's interesting already that the square root of the determinant of the Laplacian is appearing here. Okay. So essentially, I want to mimic this definition in the continuum, but I'll have to be very careful. First of all, what is the green function in the continuum? So let's take a domain of R to the D, and there is something called PT D X and Y. So that will be the transition probability of Brownian motion. Let me take it to be speed 2 Brownian motion. Killed when it leaves D. Okay, so we have a domain D like that. Here's a starting point X, and we start a Brownian motion, which we kill when we leave D, and I call PTDXY the probability that the Brownian motion starting from X is at Y at time t, or very near Y at time t. It's a derivative in Y, and has not left the domain D by time t. Okay, so this is something that is not complicated to believe makes sense for a Brownian motion. And we're going to define the green function from it. I define the green function by simply integrating this transition probability, integrating over time. So why? So recall that in a discrete, our little g of x and y was the expected amount of time spent at y before being killed. So maybe I write this like that. And if I apply Fubini, you see that one way to say it is that it's the integral also of the transition probability. So Ps of x and y, maybe I write it like that, simply just the probability xs is y and we have not touched the boundary yet. So you see that the green function, if I apply Fubini, has this expression where I simply can write it as an integral, really, of the transition probability of this random walk. So the probability that starting from x, it's at y at time s and has not been killed yet. So in a continuum, you want to mimic this definition, and you take exactly the analog. It's just that this probability to go from x to y is replaced by transition probability. Transition density, exactly. Yeah. Sorry. So let me say a couple of facts about this. So let me take d equals 2, the dimension being 2. First of all, okay, it's not obvious that this integral converges. So it's, for instance, there's kind of two problems for this integral to converge. There's a problem at t equals 0 and a problem at t equals infinity. Both of those things are not completely clear. So for instance, if x is equal to y, ptxx in any domain looks like 1 over, I guess, okay, with my convention, I guess 4 pi t. This actually is strange. But I think that's right. No, it's 1 over pi t or 4 pi t. By the way, I took a Brownian motion with speed 2 because I want the generator to be Laplacian and not half of the Laplacian. It's just to be more consistent with analytic conventions. So I think it's 1 over pi t. I'm not completely certain. Constants are always annoying in this story. So it's either 1 over 4, 1 over 2, or 1. Okay, I don't know. One of those three. But you see that if I try to integrate this, there's clearly going to be a problem near t equals 0. So that's always going to be true. G dxy is never going to be defined on the diagonal on x equals y. And even if you take x different from y, there's no guarantee that this integral converges at infinity. So for instance, if d is the entire plane, then that's not an asymptotic but an equality. And then there's also a problem at infinity. And in general, if your domain is not bounded, for instance, or as soon as the domain is kind of too big in a certain sense, then this also will diverge at infinity. Okay. Okay. So, but let me say that if D is what's called regular, and by regular I don't mean that it has a regular, smooth boundary or anything like that, but I mean that okay, I will define that. I will define in a second. Then g dxy, I claim that g dxy is finite for all x different from y. So what does regular mean? Means there exists a point z on the boundary such that starting from z, the probability to leave D immediately, so the leaving D, is 1. So we are, if I start from Z, I'm guaranteed to leave D instantaneously. So that's what it means to be regular. It has nothing to do with smoothness of the boundary, but it's in a certain sense, it means that the domain has a complement that's big enough. You can think of it like that. Okay, so let's forget a bit about this. This is a slightly technical thing, but for most interesting domains that we will encounter, the green function is something that's going to be finite for every point x and y that are not equal to one another.
Does this apply some kind of concurrent equality?
This condition of regularity, no, it's not. It really has nothing to do with sort of analytic regularity in any. It could be very nasty. Something like that. If you want an example of something that is not regular, you can imagine taking the whole plane, for instance, and removing a finite number of points. That will not be regular, because if you start from these points that you've removed, they're on the boundary, but you don't leave the domain immediately because these points are polar in 2 dimensions. Okay, so this is a slight annoyance. I told you that as soon as you move into the continuum, there's all kinds of annoying technical details that one has to worry about. That's one of them. But okay, so so for most domains, they have this property. The complement is big enough, and so the green function will be well defined. And as y tends to x, so I was hoping with my normalization it should be that, but so as the points get close to one another, so that's a 2-dimensional fact in 2 dimensions. The green function blows up. And how does it blow up? How does it blow up? Logarithmically in the distance with a certain constant factor in front. Okay, so that's...
So you're putting the green function negative now?
No, it's not actually. So why? There's a 1 over here, 1 over the distance. It's mine. It's 1 over, yeah? Okay, let me write it as 1 over x minus 1. Okay, so to the first order, the green function blow up in a way that is logarithmic. And we can say actually much more about this correction here, but that's not so important for now. Okay, so that tells us, so, you know, I would like to say that the Gaussian free field phi of x in D is a Gaussian random function, by which I mean that when you test it at x1, x2, xn, you get a Gaussian vector with covariance right, so the covariance of phi of x, phi of y should be given by the green function. That's the definition I took in the discrete, and it's the most natural thing to try in the continuum. But I see that this is a problem, okay? Because if I take y is equal to x, I'm going to have infinity on the left-hand side. But on the right-hand side, this is supposed to be the variance of phi of x. And I cannot have a Gaussian random variable whose variance is infinite. That doesn't make any sense. Okay, so this is the first hint that Gaussian free field, you cannot define it pointwise. You have to think of it in the sense of generalized function. And so this is the second of these annoying technical issues that one has to worry about when working with a continuum GFF. So I would like to say this, but I cannot, because that's just not a valid choice of covariance in the continuum, because it's infinite when x is equal to y. So I'm going to have to work a bit harder at that. So instead, what do I do? So what we're going to do is we're going to be able to integrate the Gaussian free field against test functions, let's say, or in fact, even things that are less regular than a test function. But maybe okay, yeah, maybe let me do that now. Okay, so here's what we're going to do. So I'm going to consider M plus. So this will be the space of measures. So radon measures. So nice measures. On D. Such that the double integral, so of the green function, rho dx, rho dy is finite. So the space of random, so these measures I call them rho. Okay, so I consider the set of measures for which it's possible to integrate the green function. Okay, so this, you can think of this as being some kind of logarithmic energy. Of the measure rho. So for instance, Lebesgue measure, is that in M plus? So can I integrate log of x minus y? Really the problem is about integrating close to x equals to y. Can I integrate log of 1 over x minus y in 2D? Yes, right? So integral of log r blows up, but very, very slowly. There's no problem. So, okay, what about something with which is so a function with smooth and compactly supported? So a test function. Is that in M plus? Yes, right? I mean, we try to integrate f of x, f of y, dx, dy, times the log of x minus y. But f is bounded, so we're back to the previous case.
You have to explain why on the diagonal there is not a problem.
Okay. Yeah, sure. So really it boils down to the fact that 1 over log x minus y, dx, dy, it's a very nice function to integrate. I mean, you can try to do it in polar coordinates, and you will be integrating something like r log r, right? Which is very integrable. There's no problem. Okay. But not everything is. So if I take a Dirac mass at the point x0, is that in a space M plus? No, because I'd be looking at log x minus y when x is equal to y equal to x0. So that's no. This space of measures will be things against which we will be allowed to integrate the Gaussian free field. So it includes any test function, doesn't include a singleton, but it includes a lot of things in between. So for instance, if I take, let's take a circle. So here's the point x0, here's my domain. Let's take a circle around x0 and consider the uniform distribution on this circle. So let me call that Okay, so we have here some epsilon, and this is the uniform distribution on a circle of radius epsilon around x0. So I claim this is in M+. So let's think a bit about it. Why is that true? So I would have to integrate log over x minus y, where x and y are uniformly distributed on this circle. So I could fix one of those points. Right? I do by Fubini, I fix the first point, and then I have to integrate log of the distance where y is uniformly distributed on a circle. But log is an integrable function in one dimension, so there's no problem in integrating that. Is that clear? Everyone agrees? So the Gaussian free field will integrate test functions. It will not integrate, I cannot test the Gaussian free field at a point, but I can test the Gaussian free field on things that are much more singular than a smooth, compactly supported function. So I'll be able to integrate it on a tiny contour like that. In fact, any one-dimensional curve will do. Does that make sense? So smooth one-dimensional curve. Is that okay with everyone? Should I re-explain this argument, or is everyone happy with that? Okay, so more generally, any smooth density on a smooth curve will do. Right, so the only thing that I require about rho is that it's kind of sufficiently spread out. It doesn't concentrate too much near one point, basically. Okay. Then we're going to call M to be the space of rho, which can be written in the form rho plus minus rho minus. So far everything was positive, but I don't need to restrict myself to positive things. And that will be the space of measures against which we will be able to integrate the GFF. Okay, so I'm going to define the Gaussian free field as all these random variables, the set of all these random variables where I integrate the GFF against some measure rho in M, some assigned measure rho in M. So to do that requires a bit of probabilistic abstract nonsense, but actually it's really not nonsense in this case, in my opinion. And it's worth kind of rethinking about this. So we have to kind of remind ourselves what is a stochastic process. So a stochastic process, or xt, t indexed by I, is really just a collection of random variables indexed by I. If I want to construct a stochastic process, what I need to do, so there is kind of an old recipe going back to Kolmogorov. This old recipe tells you if I want to define a stochastic process indexed by I, where I can be anything. So I is absolutely arbitrary. Often you think of time, but in this case, I will be this kind of huge space of measures. So Kolmogorov tells you if you want to define a stochastic process indexed by I, all you have to do is it suffices to specify what's called the finite dimensional distributions. So this will be the distribution of xt1, xtn, where t1 through tn are arbitrary. N is arbitrary, and t1, tn are arbitrary. So if I want to specify this whole stochastic process, all I have to tell you is what is the distribution of xt1, so just a finite number of them. And I have to do so in a way that is consistent, so that if I change from n to n plus 1, and I consider the distribution of xt1 through xtn plus 1, then that, if I restrict that to xt1 through xtn, it should be the same as what I would have given you for this vector. So these choices, they have to be consistent with one another. But as soon as that's true, Kolmogorov tells you, this is the dreaded Kolmogorov extension theorem that I think every graduate student learns, maybe in probability, but soon forgets because it's kind of very hard to understand what's going on. So here it will have an incarnation that is very meaningful, I think. So as soon as you specify these kind of finite dimensional distributions in a way that is consistent with one another, Kolmogorov extension theorem tells you I can speak of an entire, there is a single law on all such stochastic processes. Okay, that corresponds to these finite dimensional distributions. So in our case, we will have a Gaussian stochastic process. So these finite dimensional distributions, they will be specified by me telling you that they are Gaussian, jointly Gaussian, and so I need to specify the covariance matrix. And as soon as I do that, they are automatically consistent with one another. So the process of specifying a Gaussian stochastic process indexed by I is reduced to the process of specifying a covariance function. So here S and T are in I. B, function on I squared. And all I need from it is that it's a positive definite. So that means for every lambda 1, lambda n, sum of lambda I, lambda j, C of Ti, Tj should be non-negative. This is for all choice.
So how different is it from saying that you have a not orthonormal basis of a Hilbert space?
Okay, I'm going to come to that. It is actually quite different. Okay. Yeah, I will come to that in a second. So, but as soon as I give you such a covariance function, that enables me to specify finite dimensional distributions. So I just take a Gaussian vector whose covariance matrix is given by this C, and it turns out that automatically these laws are consistent with one another. So Kolmogorov's extension tells me, boom, that's it. I don't need to look further. There's a stochastic process corresponding to this covariance matrix. So the Gaussian free field will be defined like that. So let me call it phi indexed by rho. which is Gaussian. And expected value, so the covariance of phi rho prime is, well, this double integral. The sort of mutual energy of rho and rho prime, logarithmic energy of rho and rho prime. So I didn't verify for you that it's a positive definite, but maybe it's not hard to believe me that it's the case. And the Kolmogorov extension theorem tells me this really exists. I can do that. As soon as I specify this covariance, I specified really a Gaussian process. And so I can speak of the Gaussian free field, and now rho is allowed to be any of these measures. So one thing that's not hard to see is that this stochastic process indexed by rho almost surely satisfies the relation that I would need for it to be linear in rho, but almost surely. Okay, so for all lambda and mu in R, for all choice of test measure rho and rho prime, we have that phi tested against lambda rho plus mu rho prime is almost surely equal to lambda phi rho plus mu phi rho prime. So this is an equality between, an almost sure equality between real random variables. And it's not complicated to see because you would check that the variance of the difference is 0, and we're given the covariances of this thing, so it's an easy computation. It boils down to the fact that this is linear, is bilinear in rho and rho prime, these covariances. And because of that, so with an abuse of notation, we write that phi rho, we write it, as if it was, as if phi was a distribution and we were integrating against the test measure rho. So I'm going to come to your question soon. Okay, the problem is that this is satisfied almost surely for a fixed choice of rho and rho prime and lambda and mu. And there's uncountably many such choices. So I cannot say that it's true simultaneously for all choices of lambda, mu, rho, and rho prime. And so a priori, even though this relationship is almost surely satisfied, it does not really tell me that phi is a distribution.
But this almost sure comes from the Kolmogorov issue, right? And if you make the right choice in the extension, then you actually can make sure that it's equal, right? Okay,
so a priori, there's no obvious reason why there is a natural choice of extension. So it can be done. So it can be shown that there is a version of the GFF, which is actually a distribution. In fact, more precisely, which is actually a distribution. So that if rho was really a smooth test function, then this would really coincide with the notation of distribution, and we would be happy.
What do you need of a distribution? It's just a function along smooth functions.
Okay, it needs to be linear on smooth function? No, I've not said it's linear, because it's almost surely for a fixed choice of rho and rho prime, and it needs to be continuous in the test function for it to be a distribution. I've also not said that. But yes, it strongly suggests that you should think of it as a distribution, and in fact, it can be shown. So the way you show this is by doing a bit what you were saying earlier. which is that if you try to construct a Gaussian vector in Rn and I give you the covariance matrix, there is a natural way to build it by considering an orthonormal basis with respect to the bilinear form defined by the covariance matrix. And so you would write it as a series, as a sum of independent Gaussian times not eigenvector, times orthonormal basis of this with respect to this covariance matrix. So I could have done this in a discrete case, but because of time I didn't. If you kind of write it informally at first, thinking about the discrete case, it is natural to guess that phi can be written as the sum n equals 0 to infinity xn fn, where xn are IID standard Gaussian coefficients, and fn is an orthonormal basis. So with respect to the covariance matrix of this thing, and you will not be surprised to see that this has something to do with the Dirichlet energy. So with respect to a scalar product given by integral of gradient f, gradient g. And so this is another way to say this is that this is an orthonormal basis of the Sobolev space H01 of D. So these are functions which are in L2 and whose weak derivative is also in L2. So you guess an expression like that, and in fact, this series almost surely converges, but not in a space H01. Still, it converges in a sense of distribution. So it almost surely converges, I should say. Now this is really against all test functions simultaneously. In fact, it can be shown, so this is, let me write it like that. It can be shown, so this is an analytic thing that's maybe we don't get into the detail of, because I want to say something interesting. And it converges in every negative Sobolev space. So that's saying, that is saying it's not quite a function, but if you integrate it epsilon amount, it would be a function. And that's why it's actually a distribution. So it can be turned into a distribution when you think of it as a random series. That is a natural guess that you can make when you think of the discrete case. Okay. So that's for the construction of the GFF. And I would like to say at least one interesting property because it connects various things. So the GFF has a very natural domain Markov property. So let D be in R to the D, let's say. So U is going to be a subdomain. And the theorem tells you that we can write phi as the sum of two things. So phi 0 plus u, where, first of all, these two bits are independent. So phi 0, when I restrict it to the subdomain u, then it's actually a harmonic function. No, phi 0, sorry. Phi 0 will just be a Gaussian free field in U and 0 outside. And U is the one that's actually harmonic in U. Okay, so inside U, I write it as a sum of two things. One, which is a harmonic function, so think of it as the harmonic extension of the boundary data, the boundary values of the field. And this thing is an independent noise, and it's just an independent zero boundary condition Gaussian free field, extended to be 0 outside. So maybe I can show this picture. Richard, is it possible to do that? Yeah, exactly. So my experience is that it's a bit hard to absorb this theorem until you see a picture that shows what's going on. Okay. There we are. Okay, so here is your Gaussian free field on a big square, and I'm going to apply the Markov property in a case where U is a slightly smaller square. So I write it as a sum of two bits. One is this phi 0, which is a Gaussian free field in the smaller square extended to be 0 outside. And U is the rest. So because it's the rest, U is actually outside of the square, it actually coincides with our original GFF. And inside that square, it is actually given by a harmonic function. Okay, so this kind of screen encapsulates what is the Markov property of the Gaussian free field. So the reason you have to think of it as a Markov property is as follows. So suppose I were to condition on all the information of the GFF outside of the square U. So that information is completely contained in the function U, right? U contains no more and no less information than whatever phi is doing outside of this subdomain U. Okay, so if I condition on the values of the field outside of U, I get exactly this function, I get exactly the same information as this function U. And the theorem tells us, conditionally on that, well, phi, we can write it as phi 0 plus U. So U inside the domain will be just the harmonic extension of this boundary data, of whatever we've conditioned on. So this is like the conditional value at every point of the field, given the information outside. That's actually a harmonic function. This is not a surprise because the GFF tries to be harmonic. Okay, it tries as hard as it can. So if I condition on the values of the field outside of U, the mean value everywhere else will be a harmonic function which interpolates, it's a harmonic interpolation of the boundary data. But there's more than that. There is also a fluctuation term, and these fluctuations are given by an independent Gaussian free field with 0 boundary conditions. So the conditional law of the field given the values outside of the square U is given on the one hand, by the harmonic interpolation of the boundary data, this little function u here, plus an independent noise term, which is just zero boundary GFF in this smaller domain. Does that make sense? Questions about this? So, you know, the statement is quite clean, but the way we understand this statement requires some work, I think, to try to translate it into something that's meaningful. And the way it's meaningful is this, okay? So U is the harmonic interpolation of the boundary data, the harmonic extension of the boundary data. We know that because it's harmonic everywhere in U, but it's equal to phi outside. And on the other hand, phi 0 is something that's independent of that, and it's just a zero boundary GFF in the smaller domain. Everybody's happy? I'm happy to talk more about this.
But for this, what are the conditions on U2, which is also a good domain, right? Or
Yeah, exactly. Yeah, exactly. Okay, good. That's all. That's all I wanted to show on this picture. Can I turn this off? Yeah, it's just here. Thank you. So let me make a couple of comments about this domain Markov property. So the GFF satisfies not only a domain Markov property, but it's not hard to see. The green function in 2 dimensions is conformally invariant. And therefore, the Gaussian free field is also conformally invariant. We won't have the time to say much about that. It turns out the converse is also true. If you have a random distribution whose law is conformally invariant and satisfies a domain Markov property which basically mirrors this, then effectively this random distribution has to be the Gaussian free field, or a multiple of the Gaussian free field. So if you like, so this is a theorem of myself and Ellen Powell and Gurab Ray. And if you like, this is a sort of a field analog of Oded Schramm's characterization of SLE. Okay, that's one thing, one comment I wanted to make. And I wanted to make another comment. I think there was something else too, but let me show this in a couple of minutes, because I think that's a very nice application of the domain Markov property and really gives us a strong understanding of what the Gaussian free field looked like when you kind of zoom in near a point. So this is the notion of circle averages. So we can call, so for Z in a domain, and epsilon small enough that the ball of radius epsilon is contained in the domain, I can speak of phi epsilon of Z, so that would be the average value of the GFF at distance epsilon from Z. Okay, so I take a small circle around Z, and I integrate against the uniform distribution. We've seen that it makes sense to do that on a small circle around Z. So you can think that this is a way of regularizing your Gaussian free field. For every point Z, you take the average value of this Gaussian free field at a small distance epsilon. And you can ask yourself, as you send epsilon to 0, what happens to this quantity? So here's a very nice theorem. It tells you that, so let me reparameterize these distances by e to the minus t. And the claim is that this is actually a Brownian motion with some variance, probably 1 over 2 pi. So as I zoom in towards the point z, and I sort of consider the average value at a distance that's smaller and smaller, the way these average values behave as I get closer and closer is exactly the way a Brownian motion would evolve in time. A one-dimensional Brownian motion would evolve in time. And so it starts, as you send t to infinity, bt, a Brownian motion, oscillates between roughly plus square root t and minus square root t. This starts oscillating really a lot. And this gives you a very strong sense for why the values at the point z cannot be defined. If you want, the values of the field at various points z, it's like plus and minus infinity everywhere. From that point of view, it's kind of a miracle that you can define the Gaussian free field, that when you integrate against the test function, all these plus and minus infinities, they kind of cancel one another, and you get a finite value, Gaussian, with a Gaussian distribution. It's a miracle, really. Right? So this really tells you, locally near a point z, it's, you get very high value and very negative values. I'm claiming this is a very nice application. I have maybe 1 minute, no? No, I'm out of time. Okay, so I won't say how that goes, just to say that this is a very nice application of the domain Markov property. You would verify that this as a function of t has independent and stationary increments. The independence is really a direct consequence of the domain Markov property. The stationary of the increments is a direct consequence of conformal invariance, in fact, scale invariance. And the fact that it's Gaussian tells you that therefore it has to be a Brownian motion and centered. And you just have to identify the variance, but we know how the variance locally blows up, so it's quite easy to do that. Okay, I guess that's good for today. I think tomorrow Evelina will talk about SLE and maybe some connections between Gaussian free field and SLE. All right, so thank you very much.